All right, thanks everyone for signing in. We're going to start with chapter 13, which is classification and regression trees. Let me just pin my video here and reduce screen size. Okay, cool. So far we've talked about models that incorporate this global perspective where each point contributes somewhat to the data collection, to the parameter estimate. And in this case, like we start looking at ways of dividing the data set um, to use subsets of the data for piecewise prediction. And essentially, what he's saying is you want to partition the data set so that each prediction will use only points from one chunk of the space. Why is this beneficial? Well, because some points are really not related to other points, and they don't really help in making predictions. So why consider this global perspective? And to some extent you can push back on that by saying, well, but like we weight some point zero, so when you consider nearest neighbors and techniques that include like these piecewise polynomials fitted to specific data points, then sure, you're weighting some point zero, so you're not using all the points to fit the model. But in general, he's talking about comparing linear models to trees, where trees actually partition the data set into subclusters before into subsets before using those subsets to fit models specifically to any other points that fall into that regime. So um yeah, I mean, nearest neighbor still like figures out the best cluster and then does that. In this case, it just falls into different subclasses, so somewhat of a distinction. But yeah, I don't completely buy this premise that we've only worked with models in a global sense. So yeah, the idea is to partition the data set so that each prediction uses points from one chunk of the space. And the chapter is about how do we arrive at this partition? What is the best way to define partitions? Because you can imagine there are n numbers of ways to define partitions of a data set. Yeah, I don't want to switch to Bluetooth. Okay, cool. So these may seem too crude to actually work, but in fact, this tree-based approach of partitioning this dataset can actually be powerful and computationally efficient. Efficiency is just a function of you reduce your number of data points to fit the models. Um, and this section is about discussing like how exactly we are doing this. Well, you have a certain starting point where you select how you want to divide the data. So um, if you have this stage one, which is 5 points in your data set, you ask some question and you divide them into red and blue. For the red ones, you further ask some question and you go from light violet and light purple and dark purple as an answer to that question. From blue, you go to green and dark blue, and from dark blue, you go to black and gray. So again, this is a byproduct of the kinds of questions you ask. And the natural next question you have is, okay, then like how do you choose which questions to ask? Well, you start to think of a way that I don't want to, I guess I'm skipping a few sections, but I'll mention that anyway. You want to find a way to divide it such that you are left with the least uncertainty in how to divide these points. So like you want to maximize this information gain, or maximize this reduction in entropy. Entropy is uncertainty. Um, or yeah, entropy is uncertainty, and you want to reduce your uncertainty about dividing up your data, which is why the best questions will be the ones that reduce the uncertainty the most. And mathematically, we'll get to a breakdown of that. But before that, let's look at some concepts of like what is a tree, what are the different parts of a tree. So terminology. So um, okay, the motivation and another important aspect of why we use trees is because trees are very interpretable. So it's very intuitive to figure out what question, because we know what questions we are asking. It means I can actually understand why this point is on the left and that point is on the right. So, and by left and right, I just mean this red and blue out here. This. Okay. Or at any different stage, the questions. So interpretability is big with trees. Um, and even though they might have complicated non-linear ways of interactions, trees actually work surprisingly well in practice. So compared to non-parametric smoothers, I mean, it's a fair approach to say just dump it into a non-parametric model, fit some model to it, and like discover the non-linear relationships between variables. Sure, you can do that, but that doesn't give you interpretability. So using trees gives you some notion of interpretability, because then you can at least see my data is divided into these sorts of spaces for these reasons. Okay. The terminal nodes in a tree are called the leaves. These terminal nodes represents a cell of the partition. So this is a terminal node, this is a terminal node. And like you might imagine, if there are more points here, yikes, they might fall into one of these categories, like go through this point might go through this and end up here, this point might end up here. So like it's not just a single point, but in the limit of dividing things up, you can go down and learn a tree for every single point. Learn a tree that has a leaf corresponding to every single point. We'll get into the challenges of that and like where that is useful a little later, but that was just illustrative of like, this is what a tree can do, this is not what we want a tree to do, not necessarily all the time. Okay. So recursive partitioning, nice interpretability, ask questions until you can divide it into different categories. Questions should maximize your information gain. Okay, now let's take an example of why a tree might allow us to have interpretability. A short note on India versus the US in terms of presidential versus parliamentary forms of government. The elections in the US are like two-stage. There are two main parties, the Democrats and the Republicans. Within the Democrats, for example, there are like 10 candidates that stand for getting the Democratic Party nomination. So it's like saying Manmohan Singh and Rahul Gandhi and Sonia Gandhi all stand and compete to get the Congress nomination. And then they would go up against Mr. Modi. So that is the style of government that they have in the US. So here they're just representing this Obama Clinton divide. So anyone who is registered to vote as a Democrat, and that's a whole different concept, but like for among people who vote for Democrats, they vote for whether they would choose Hillary Clinton or Barack Obama. So that is what they're showing here. The questions are highlighted in black. The answers are highlighted below it, and based on the answers, this is a binary tree. So a yes no answer suffices. You can think of like a general tree with many different answers, like one of k choices, but you can always reduce that tree to a binary tree with more layers, with more levels. So that's why this is like the I guess popular version of tree. There are some other properties that I've highlighted later, we'll get into those. But yeah, that's why we'll work with binary trees for now. And you can start seeing that, okay, these questions actually start making sense, there are some patterns. And once you get more counties, or once you get more people, you can start figuring out which bucket they fall into, which leaf node they will go to, right? And then figure out, okay, these people are likely to vote for Obama versus Hillary, 56 to 35, or maybe Hillary versus Obama 48 to 13, depending on how they answer. So again, like this photo is attributed to the New York Times. And what do I want to say about this? I feel like this is straightforward. There are categorical variables and there are continuous variables. For continuous variables, typically the questions are like, does it fall within a certain range or beyond or below a threshold? For categorical variables, it's easier to ask yes or no questions. So that is fine. Again, we mentioned this already. You could do more than binary questions, but that can always be accommodated as a larger binary tree. Asking questions about multiple variables at once, again, is equivalent to asking multiple questions about single variables, which is pretty important. Okay, why binary trees? It has nice properties. For example, it combines the properties of ordered arrays and a linked list. So for a linked list, insertion and deletion is fast. For ordered arrays, search is fast. In a binary tree or a binary search tree, if you will, um, all three of these are fast. So it combines some nice properties, although tree deletion is like there's a complex algorithm to write for it because you need to handle the subtrees and associate them to the nodes above. Anyway, um, currently we're going to talk about this model in the leaf node. So like we said, this point, the yellowish orange points might fall into any of these buckets. And for any node that falls into these buckets, we will just average the predictions of the training data. So we have training data xi, yi, and suppose y1 and y5 fall into this light purple bucket here. This is, then we just, for any point that falls into this bucket in the test data, we just return yi plus y5 by 2. So we take a simple average, which is like a piecewise constant function. So you start seeing that, okay, so for any point x's that fall here, you return this y. So for some range of x's, you will get some y. Not some y, you will get this y. This is the value at this point. Okay. For some other ranges of x's, you will get some other value of y. And that starts reaching this point where, okay, now this is what you mean by piecewise constant functions. So this is on the x-axis, there is a piece of x here. There is another piece of x here. And piecewise, the y remains constant. So that's what they're trying to say. But anyway, I've drawn a better diagram of this later. So, or maybe I'll just leave this in here. Why not? Okay, cool. Enjoy. So, Obama-Clinton divide, piecewise constant and piecewise linear. You can imagine that now if we have all these yi's and xi's, you can also fit a linear model to each leaf node. And that linear model can have different parameters. So that can be a slightly better version of fitting these models. Okay. Trees can be compared to, okay, before that, interesting advantages. So handling missing data. If you don't have some x's, you can just stop there. After some node, you don't have the answers, right? Just average all the y values below that node, pick out all the data and return that. So even though you might not have enough data to make a good prediction, you do always have enough data to make a prediction. I don't know what to say about the accuracy, because like for any given model that you have fit, you can always make a prediction, like just randomly pick a value. But I don't know. Yeah, I don't know what to say about whether that's a really good thing or a bad thing, but at least like you're using some information available to you to make that prediction. Model gives a jagged response. So by jagged, it's just that this is not a smooth function. If it is smooth, though, the piecewise constant surface can approximate it arbitrarily closely with enough leaves. So if you divide x up into enough sections, then this can have different values per section, and then you end up with like this function. which actually can approximate any. So you have, sorry, here it goes like this, 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 yes. So like you're basically creating a very pixelated version of a smooth function, which means if you have enough pixels, you can create a very nice image, which means you can start approximating things well. So let me know if this is unclear. I will pause for a second also for other questions. So you can start approximating something like this very nicely. With enough x intervals, you're doing well. So that's what they're trying to say. Um, I really wrote over my piecewise constant, so I should probably erase piecewise constant here. Okay. Maybe I'll just point this to this and to this. Cool. Okay, so comparing it to k nearest neighbors, the limitations of KNN is there is a fixed k, firstly, and secondly, the similarity metric. So you measure k typically based on some distance from other. You're measuring the distance in terms of your inputs x, and you're ignoring the responses y completely, which is not fair because the responses might reveal something about the structure of the data. So yeah, you might want to account for the y to obtain the similarity metric for which you receive, for which you define the neighbors, using which you define the neighbors. Cool. Sorry about that. So prediction trees are in a way adaptive nearest neighbors methods, because they start creating these neighbors, but not only based on x but also based on y. I guess so. Maybe I'm missing something because in my head most of the questions were asked about the x. So all of the questions had to do with the x and not the y. So how are we really improving on KNNs using trees if you are saying you're only using the x's, not the y's? Well, I guess. Yeah, I actually have this question. Maybe I don't know if someone can answer it for me. So my question is, they're saying KNNs improve, trees improve on KNN because KNN is defining similar entirely in terms of inputs, not the response, right? Oh, he's answered it in the next line, right? Trees get around both problems. Leaves correspond to regions of the input space, but one where the responses are similar. So I guess the inputs are the questions, the responses. How
Could
do
it
you?
be that?
Yeah, go ahead.
Is it?
Could it be
Is
that
it? Yeah. Sorry.
Jay, go on, it's fine.
So is it like based on like the cart sort of tree, like where we have like this distant boundary? So based on, but again in that case also, respond we segregate based on like the entropy values. So like your the response in a class doesn't like not like actually it matters, but yeah, for calculating all that.
I think this is a great point. I think
But
the math will explain this to me better because yeah, when we get to the entropy and conditional, yeah, this is a great point. Yeah, I'll get back to
but
this.
So,
in entropy also we are using the response variables only, na? Like basically for class labels as such. So it is technically using that.
Yeah, exactly. But I was saying it'll become. I haven't mentioned anything about entropy so far in mathematical terms, so it'll become much clearer once we get to like, okay, what is entropy? Which variable is it defined in terms of?
Mhm.
I think the split is generally defined for random forest. I think the split is generally defined based on the average loss function. Would it be that?
Did you break off or did you mute yourself?
Yeah, sorry, I broke up. So could it be that the a dependent variable y is used in that those terms of seeing how much the points deviate from the mean loss?
Yeah, I think that is exactly at the end. We define the entropy of the variable y, and the conditional entropy condition on answering some questions a. Again, I don't want to get into that before we do the math, but I think that to me makes it much clearer as to why the responses are used. Okay, thanks a lot for that discussion. That was really helpful. Okay, he gets into an example that I'm not actually going to highlight very deeply, but I will go over it in brief. This is about predicting house prices from certain variables. In R, if you remember, this is like the Y. The way we write a linear model was linear model LM of Y, which we regress on your variable x1 and your variable x2. So it fits a model y is equal to beta naught plus, sorry, beta naught plus beta 1 x plus beta 2 x2. That is what you're essentially saying in terms of the syntax. It just makes life very easy. So that is what you're doing here for the tree. You define your y as your log house value, and you define your x1 as your longitude. Let's say L1, and we have L2. Cool. So your y is regressed on L1 and L2 using this function. And once you fit the tree, it tells you that okay, my root mean squared error is equal to root over the squared residuals, which is 0.41, which is not as good as, well, if you've read this example, then non-linear models do better, which is not surprising because non-linear models are designed such that they capture these nonlinear relationships, and trees are not really capturing all of the nonlinear relationships. But the super important advantage of trees is now everything is interpretable if we fit it to the tree. Also, this is like a very simple tree because we're using only two variables and we have only 12 leaves, which is like, leaves are indicative of like how many questions you have asked to get to this point. So 12 leaves is indicative of like we haven't asked a lot of questions. Like, by itself it's not indicative of anything, but as you start reading further you understand that okay, we can actually have 60 plus leaves. So we're clearly asking very few questions to divide the data up, which means we're not like being very granular in highlighting the different patterns in the data. So clearly that indicates that we don't have a great error, but it's still pretty decent even without all of this complex tree fitting. Even with the bare minimum tree, we're doing reasonably well. So how do we fit more complex trees? Well, you allow it to ask more questions of your data, start dividing the data further and further into more parts. And I had a diagram highlighting this, I thought. Oh man. Okay, I guess it was very further ahead. Basically, I'm saying like, how do you decide where to stop? Like we saw originally, we start with yellow points. We ask one question, divide it into two parts. Ask another question, divide it into three parts. Ask another question, divide it further and further. So like, how do we decide at which point to stop? Because technically we can do this until at this point, each of the points is a node, right? Light purple, dark purple, black, gray, and green out of our original 5 points. And that is really not ideal because there has to be some pattern. Here we are saying every point is different, but then we're really not learning any pattern. So one, okay, I'll get into the algorithm later. This was just highlighting where to stop. And because of the need for that, we use this concept of did someone say something? Okay, I'm assuming not. If you did, feel free to unmute. Okay, so otherwise you might have a leaf per data point, which beats the point of pattern recognition. So in order to actually add a node, we place this condition that adding this node has to reduce the standard error by at least a certain amount. And we'll look later at how we define this error. Um, so the default for min deviation is 0.01. If it does not reduce the error by at least this much, then we do not add that question and therefore the resulting nodes. So with longitude and latitude, we start seeing that, okay, first it asks a question about latitude, then a longitude, then a certain latitude, then again a certain latitude. So figure out like what criteria this falls into. Um, and then eventually we arrive at some house pricing distribution. Okay. And the beauty of like using R is you literally just use this one function called plot tree fit, like plot of tree fit, to obtain this nice looking plot that tells you basically all you need to know about how your data is being divided. um R really like does well, much better than Python, I believe, when it comes to statistical analysis, and it makes sense that it is the tool of choice for most statisticians. Especially when it comes to causal inference, R is much further ahead than Python, at least in my opinion. Having been a naive user of R and an experienced user of Python, but we're getting there. Okay. Anyway, back to the point. Like the same thing, you can plot and you can look at what the ranges of y values are for a certain input range. Oops, sorry. The y values are highlighted in black. So this is the x1 and x2 values, and the y, I assume, is the class label. So there are like what seems like multiple different shades. Oh, y is a continuous variable. That's why the multiple. Okay, got it. Oops. So I think darker is more expensive houses. I don't know if it's mentioned here, but the code probably makes it clearer. Color equal to gray, cut dot prices, PCH. Think I'm not sure what this line means, but I assume they're picking a higher price is the darker gray. Um, okay, anyway, so you can see that the tree divides the data based on some questions it asks about the latitudes and the longitudes into certain buckets. And that can be easily visualized on a plot like this. Of course, more than two variables, it becomes more difficult to visualize it. Yeah. But you can always pick two variables and visualize them. So this goes back. Okay, now think about allowing for splits that don't actually give you much noise variance. So like we said, how do you decide where to stop asking questions? Well, what if you don't? What if you ask as many questions as you like? Well, then you get this sort of diagram which clearly is not interpretable. You're going to divide it as finely as possible and end up probably with a node for each data point. So yeah, someone came up with this idea. So this is the corresponding plot for that, dividing the tree up into multiple different sections. Especially if you look here, you see that it is definitely unintuitive, like how as to whether there is any pattern here. But some but this is definitely less biased because this allows you to learn any pattern in the data that is present that a non that less biased. What do I want to say more about less biased? Less biased is saying you're closer to the true function, but the cost at which that comes is a much higher variance, because if you change something a little bit, you're probably going to have a very different redistribution. But that is, I don't think that ties into less bias. That ties into higher variance, but perturbation. We'll get into this. I'm jumping a bit ahead of myself and I'm skipping some concepts. Okay, so before all of that, once we fix the tree, The local models are completely determined and easy to find. We just average them, right? Like this piecewise stuff that we spoke about. So all the effort should go into finding a good tree, which is to say finding a good partitioning of the data. Excuse me. Ideally, we maximize okay, this concept first, yeah. Ideally, we maximize the information this partition gives us about the response. The response is y. The information we get about it depends on the question we ask. And so he's saying we want to ask the best questions first. Since we are doing regression, what we would really like is for the conditional mean to be nearly constant in X in our data set over each cell of the partition, and for adjoining cells to have distinct expected values. So two parts to this. One is conditional mean. So this conditional mean of the function over this cell is nearly constant. Like we want it to be nearly constant so that this red line can approximate it well. In this case, it's not actually nearly constant, but that's what I'm saying. It might not be, but we want it to be. And we also want two adjoining cells to have distinct expected values so that it is much easier for us to separate these two, like points that fall into these two buckets than points that fall into these two buckets. So that's what he's saying. Like even though like further away, different buckets might have similar values, at least closer by, when I ask x's, when I ask questions that result in adjacent nodes, I want them to have distinct y's. Okay. It's really hard to do this directly, so we start doing a greedy search. So we find the one binary question we can ask about the predictors which maximizes the information. I still haven't described mathematically the information gain of this asking these questions, so we'll get into that. But we start by maximizing that and going iteratively from there. Oops. Okay. Da, 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 da. So you keep asking questions and you define a certain stopping criteria. Again, like we discussed, this could be either that, okay, beyond this, the questions don't give us more information. So there is no reduction in standard deviation. Or you can say that after these number of leaf nodes, I just want to stop. I don't want to find more leaf nodes. So a more typical criterion is something like halt when each child contains less than 5 data points. Oops. Cool. Or when splitting increases the information by less than some threshold, that is fine. So first things first, we spoke about the standard error. What does the standard error mean? Well, in this case, remember how we averaged y, arriving at this mean per leaf. Well, the standard error then is just that mean per leaf, the y for each data point minus the mean for the leaf that it fell into, and sum that over each of the leaves of the tree. So for each leaf, for each data point in each leaf, subtract its prediction minus the target and sum that over all the leaves. That's all this equation is doing. So then the basic regression tree growing algorithm is then as follows. Start with a single node, calculate this MC and the mean squared error. If all the points in the node have the same value for all the input variables, then stop. Like if all of the points are the same, then there's really no data set in the first place. If not, then start searching over all binary splits of all variables for the one which will reduce the mean squared error as much as possible. Then you define the stopping condition that if this split does not give us more information than some threshold, then stop splitting. Otherwise, split into two different values. Then again, recursively apply this tree growing algorithm. Consider the split, consider the information gain, consider all variables. Which one should I divide with first? And then continue recursively until completion. Okay. Problems with this algorithm. Can anyone point out one problem?
Um, this is sort of a greedy approach, and there can be times when uh, if we would have taken another variable instead of splitting the same, we would have gotten a better score.
Exactly what he says later, right? Thank you. So, one natural problem is like if multiple variables are equally good, which one is chosen as a matter of complete chance. Secondly, it might stop too early, was Deep or Josh? One of them said. Um, oh, there's no Josh. Okay, that was Deep. Um, there can be variables which are not very informative themselves, but they might lead to more informative subsequent splits, which is like the flaw of a greedy algorithm, that it chooses the optimal one at this step, not the optimal one in general. Um, okay, so solutions to this. Well, one thing is cross validation, but another way cross validation can involve like subsampling and then creating trees from those subsamples and then looking at which variables are most informative in those trees and then picking that for the regular data set and so on. But another approach might be start building the most complex tree you can build. Have one node for each data point, because you can't do better than that. You can't do better than that in terms of complexity, not performance. Once you have that tree, then start pruning the branches that you really don't need. So yeah, so build a big tree and then cut down its branches. The reason this is better than arbitrary stopping criteria is that it directly checks whether this extra capacity pays for itself by improving generalization error. If it does, great. If not, reduce the complexity. There are lots of cross validation tricks. One is like alternating growing and pruning. Divide the data into two parts. First grow, then prune, then exchange training and testing sets. This is again you're doing completely with your training set. So your actual testing set is kept separately. You don't use that to prune your tree. So create this training and testing set from your training data, then switch them around, prune the tree, alternate, keep going. So this is again multiple different cross validation style approaches. Okay. Um yeah, I don't think I want to say anything about this section. This is our algorithm stuff and not really non-intuitive. Yes, this is a good section. This is an important. Did I record? I really hope I was recording. Yeah. Oh, poof. That was scary. Okay, so with a regression tree, we can separate the uncertainty into two parts. First, uncertainty assuming the tree is correct. Second, search over the space of trees to find the correct tree, if at all the data can be described by a tree. So the first source of uncertainty, imprecise estimates of the conditional means within a given partition, which is what you're averaging your y's, you're assuming this piecewise linear function. That might not be correct. Well, that can easily be dealt with, just as we've done in the past. Like what happens when this estimator is not the best and you have certain ID data. Well, different ways of doing that. But the more important question is like as the response values change, the tree itself changes, and this is not like changing in a tree cannot be defined in like this continuous space. You're defining it in a discontinuous space. When I say discontinuous, I mean discrete. So yeah, that's what I mean, because these questions are not necessarily continuous. Yeah, I guess. So what we want is some estimate of how different the tree could have been had we just drawn a different sample from the same source distribution. One way, and we just saw this an hour or two ago and before in lecture 6, is we can use bootstrapping. So bootstrap, the resampling bootstrap that we discussed, maybe that is an approach to sample data from your original data set, create these subsamples, fit trees to this subsample, and see how much the trees are varying. um I don't know what else I want to say about this. Like, it is, I think it is hard. I think I don't have enough empirical experience, maybe, but it is hard to say like whether you have the right tree or not. All you can do really is, yeah, bootstrap your data and then refit a tree to it. Okay, so far we've been talking about continuous valued y, so regression trees. Now let's think about classification, where your y is discrete. You want to predict a certain number of classes from it. Well, fairly straightforward. They just replace your all your regression stuff with classification stuff, and that's just like this last step of predicting classes instead of intervals for your y. Okay, so couple of tiny pointers there. So in classification, you want typically these probability. Okay, maybe I'm jumping too far ahead. Yeah, I'm jumping too far ahead again. So let's before I say things about that. Um, Classification trees are found in the same way as regression trees. Look for the binary distinction that gives us most information about the class. Then take each result, repeat the process recursively until you reach a stopping criterion. How are we doing on time? Okay, cool. We have 15-20 minutes left. Measuring information. So this information of y and a, where a is the answer to some question that you're asking about these variables. So a can be a range for x, or a can be a categorical question about a question about a categorical variable x. What I want to say here really is, look at this definition of this information. Information is defined as the entropy of y, the information entropy of a random variable y, minus the information of a entropy of a random variable y, conditioned on this answer. Which means what? Which means how variable is y it by itself, and how variable, or like how much, how variable is it once we know something about this particular question about the data. So if I have some sort of variance in the average students, engineering students in India, is there less variance if we know that now these students are from Mumbai University? So grades of all students in India versus grades of students in Mumbai University, does that Mumbai University aspect give me some information that reduces this uncertainty I have? Because now I know that, okay, if they're in Mumbai University, their grades probably fell between some and some criteria in the JEE, so they're this level of well trained or well prepared or whatever, and therefore I know something that reduces my uncertainty about their grades. Whereas in India, the range can be anywhere from anywhere to anywhere, in the entire spectrum of grades possible. So that is what they're saying. So this conditional entropy term is typically, or no, always less than or equal to the information entropy, because if a does not give any information about y, or if y is independent of a, then this will just, conditional entropy will reduce to information entropy. But if a does give some information about y, then this conditional entropy will be less than the information entropy. So that is the takeaway from this section. Conditional versus information entropy, and how we use that to define information gain. um, yeah, I don't think I have anything else to say. I already said all of this. And so you ask, oops, my mistake. Hey Josh. um yeah, I apologize for the time mix-ups today. That's on me, but we will have discussion about what's a convenient time for everyone and reschedule the meetings as per the majority. um yeah, okay. Okay, so yeah, this is just describing, okay, if there is a series of questions, then the last one has to be conditioned on the previous ones. Like all of them have to be conditioned on the previous questions people asked. Okay, yeah, so again, when you go from regression to classification, if you have to make a distributional prediction for each class, um, the natural problem that should emerge in your head is, but what if this leaf node does not have all the classes? Then most of the classes will have a probability of 0. Well, yes, because that you're going to estimate the frequency. You're going to use the empirical frequency of a certain class in a certain leaf node to estimate to approximate the true probability of the class for data points that fall into that node. That's a very long sentence, but bottom line being, if this node has like 3 cats and 2 dogs, then I'm going to say probability of cat is 3 on 5 and probability of dog is 2 on 5. But wait, what about elephants? Like there are no elephants in this node, so I'm going to predict 0. But that might not actually be the true probability. It might just be a function of my limited data. So, or the tree that I built. So that's what they're saying, that okay, this results in, this is the maximum likelihood estimate. But we may easily fail to see any samples when the number of classes is large relative to the sample size. So I have 5 data points and 4 classes. Well, I'm probably not going to see a class in every single node. Um, so yeah, that is one issue. Measuring error goes back to like the cost of predicting something wrong. This misclassification rate we've already seen is the fraction of cases assigned to the wrong class, but like really what I want to talk about here is average loss. So cost of classifying some examples wrong might be far higher than classifying some examples right, than other examples wrong. Predicting someone having cancer when they don't have cancer might be okay because they can verify that later, but the reverse might not be okay, because typically if someone says you don't have cancer, you're like, okay, great, go away. You don't actually go back to verify with 3 different tests that you don't have cancer. So that is a super high cost, and they get at that in this table. So please read through this example really well. um, I'm not going to go into much detail, but I will say that loss of that particular example is equal to cost of predicting it wrong into the probability of misprediction. I should not use misprediction. Is misprediction a word? That's, I don't know. But anyway, you get the point. I should say misclassification. Anyway, very, very intuitive example. Super nice. So look that up. Um, when you're going back to uncertainty now, so you want to know whether your model made the wrong call with confidence or tentatively, and those are both very different. Again, you guys know this already, so I'm not going to harp on that. The way you measure this is equal to the loss. You sum the negative log likelihood for the data. Okay, so he says normalized negative log likelihood. So this 1 by n factor, that's where it emerges. He goes on to explain that suppose you use this empirical probability. So number of observed classes as the probability of those classes. Then this n and this capital N cancels out and you're left with this probability hat. So we discussed this as the maximum likelihood estimate, right? And I was confused about this because it was first unclear to me what he was saying, and then there is this golden rule in math where notation, even if it is confusing, comes first and the explanation comes later. um I don't know, I feel annoyed by that, but I guess I don't know what's best for teaching, and a lot of people have spent a lot of years doing this, so this might be the best way. But either way, like he explains this really well later at least. So I was clear, he's explaining how we take an estimate using empirical frequency. So 3 cats, 5 dogs, 3 on 8 is cat probability, 5 on 8 is dog probability, that way, which is where this probability hat comes from. And then this reduces to the entropy. And yeah, I've made notes about this, so feel free to do that. But this gets us to this idea of cross entropy, because as it turns out, the model's estimated probability is this, and this cross entropy is always larger than the conditional entropy, because this empirical probability estimate is is not the true probability. I don't know why he said always larger. I'm pretty sure it has to do with the variance of a sample underestimating the true variance. I don't know. Maybe someone can comment and correct me, or he's given an explanation. Generally, the in-sample cross entropy is lower than its expected value. So I get like the outcome of this is that your in-sample test error is lower than your generalization error. So that is the outcome, but like the intuition for this, there is a key piece that I'm missing a little bit, but like I'm almost there. um I guess he's saying your data set will be nicer, so it will have more samples of each class than might occur in practice. But how can you say that for each class? That's my concern. I don't know. Yeah. Anyway, the convergence holds. So as you get more and more samples, this cross entropy will converge to this conditional entropy. So we should be good. Sorry, this empirical estimate will converge to the true class probabilities. So we should be fine. Yeah, cross entropy, conditional entropy. Yeah, exactly that. Okay, last section in the book, in this chapter. It typically in your training data, you try to oversample your low probability outcomes because of this idea of balancing the data set and then using that classifier. But if you try and balance these data sets and then apply them in practice, then you'll start getting equal numbers of healthy and cancerous patients, which might not actually be true, which might like really freak some people out. So what happens is, the Neyman Pearson approach classifies errors into two types, which is type 1 error and type 2 error. So if you see this plot on the side, if x-axis represents the true value of the sample, so I'm assuming a binary target, positive and negative for cancer, okay, and the predicted is also positive and negative for cancer. If a true positive is predicted positive, we are good. If a true negative is predicted negative, we are good. But this type 1 error falls when like a true negative is classified as a positive, so it's a false positive. And type 2 error occurs when a true positive is classified as a negative, so that's a type 2 error, which is a false negative. So you associate these two types of errors to alpha and beta. What he's saying is the way we find models is we fix the error alpha that we're comfortable with, we fix, and then we optimize for the other error rate. So we fix the size of the test, and then we maximize the power of the test. Just different terminologies. The intuition is fix one error and then play around with the other, minimize it, find the best model, and then retrieve that as the user, retrieve that for the user. So whew, the rates alpha and beta are properties of the conditional distributions of the variables. If these conditional distributions stay the same, but the proportions of the class change, then the error rates are unaffected. So that's a statement he's making about generalization. Like as long as these conditional distributions remain unchanged, we are good. Even though the number of classes might, the proportion of classes might change. And that's it. That's the end of the chapter. Um, yeah. feel like people might do well to read this because hypothesis testing is really, 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 really important. A lot of statistics, a lot of, I think, bandit algorithms and reinforcement learning, and I guess product related. All these decision scientists and economists rely a lot on hypothesis testing. So yeah, that's all from my side for now. I'll pause for questions. Okay. If there's no questions, I can go on and start the next meeting. I should stop recording first.